Section 2.3, Part 2, Graphs of Polynomial Functions. In this section, the goal is that you'll be able to graph a polynomial function. What we've been doing up to this point is solving polynomial functions, and you'll find pretty quickly that solving is a prerequisite skill to be able to graph polynomial functions. So everything we've done up to this point has been preparation for what we're about to do now. The first thing we need to establish is that polynomial graphs are smooth and continuous. If I have a polynomial, then its graph should be smooth and continuous. What I mean by smooth is that it has no corners, continuous meaning it's fully connected. So I should be able to draw a polynomial graph with one fluid stroke of the pencil. If I need any abrupt changes in directions, in other words, a corner, then that's not going to be part of a polynomial graph. If halfway through drawing my graph, I have to pick up my pencil just to put it back down to continue drawing, in other words, I have a break or a jump, then it would not be fully connected and thus would not be continuous and thus would not be a polynomial function. For example, if I look at this graph right here, I can immediately tell that this is not a polynomial because it has a corner right here. Another name for a corner would be a cusp, C-U-S-P, cusp, but that's just a fancy math word that means corner. So this one is not a polynomial. If I look at this one, I see that the graph is not connected. I've got the right side of the graph ending here, the left side of the graph ending here. It's not fully connected. It's not continuous. It's not a polynomial. If I look at this one, I see this curve right here is smooth and continuous. This curve right here is smooth and continuous, but I can't have two separate smooth and continuous graphs. I have to have one complete smooth and continuous graph. This one is not a polynomial either. This one, on the other hand, is one fluid stroke of the pencil. It's like a little snake curve. This is what a polynomial graph looks like. And that can kind of be what it looks like in general. You should see something that kind of curves up and down, up and down, up and down, depending on the degree of that polynomial. So speaking of our general form of a graph of a polynomial, it's going to curve up and down, up and down, up and down, depending on the degree. For instance, if we have a linear function, we generally wouldn't describe it as a curve, we would describe it as a straight line. But in general, it actually is a curve. It just is a curve that doesn't curve. It curves down, but then never turns around and curves back up. It's a linear function. It has exactly one x-intercept. Now, of course, it doesn't have to have an x-intercept. If it was a horizontal line, it would have 0 x-intercepts. But at most, a line can only have one x-intercept. If we kick it up a notch to a quadratic, second degree, we can have at most 2 x-intercepts. And again, we could have possibly 1. If the vertex was right on the axis, we would only have 1 x-intercept. Or if the vertex was above the axis, or if it was below and pointing down, we would have no x-intercepts. So again, the degree doesn't tell me directly how many x-intercepts it has, but the degree does tell me at most that's how many x-intercepts we have. There's no possible way to draw a parabola with 3 x-intercepts. Now look what happens as I increase the degree each time. We started with linear, it just pointed down, and then it curved back up, and then cubic curves back down, quartic curves back up, quintic curves back down. Every time I add another degree, it basically just adds another curve to my graph. Notice 5th degree, I have 1, 2, 3, 4, 5 x-intercepts. 4th degree had 4, 3rd degree had 3, 2nd degree, 1st degree, and so on. It can have at most that many x-intercepts, but of course it could always have fewer, depending on the actual solutions to the polynomial. For instance, maybe this curve doesn't go all the way down to the negative values. Maybe it only curves down to about right here and then curves back up. It could still have the capability of having 5 x-intercepts, but it may not necessarily have 5 x-intercepts. But in general, we can see the graph of a polynomial is like a little snake curve. It curves up and down until it runs out of x-intercepts. Now we can determine a little bit more specifically the shape of the curve as well as the number of x-intercepts it's going to have by certain features of the polynomial. The first thing we're going to talk about is end behavior. When I'm talking about end behavior, I'm talking about where does the right side end, where does the left side end? Not what's happening in the middle here. In the middle I have 5 x-intercepts. My question is end behavior as it goes infinitely to the right, does it go up forever or does it go down forever? As it goes infinitely to the left, does it go up forever or does it go down forever? That's the first question that we're going to answer, and that question is going to be answered by the leading coefficient, by using the leading coefficient test. So to explore this properly, I'm going to go ahead and pull out my graphing calculator to look at some sample problems. So if I go ahead and graph y equals x, I've got my perfectly straight line starting on the bottom left going up and to the right. And look what happens as I graph each next level of function. So I've got x squared, there's my parabola. I've got x cubed. Remember x cubed, our parent function for x cubed, that was disco guy, kind of looks like a little S curve. Now notice the cubic graph here doesn't look like the cubic graph that we looked at a second ago. Remember, a cubic graph can have at most 3 x-intercepts. X cubed, the parent function of the cubic family, only has 1 x-intercept because it's x cubed. Set x cubed equal to 0, x equals 0 3 times. So there's only 1 x-intercept on x cubed because it's the parent function. All the parent functions are going to be very simple versions of those snake curves. So if I keep going and graph x to the 4th, look what happened there. X to the 4th kind of looks like a parabola. It's just a slightly skinnier parabola. And that's generally going to happen as we graph x to the 5th. It's going to look familiar. X to the 5th snakes up just like x to the 3rd does. X to the 6th, you're going to see looks just like x squared and x to the 4th. There was x to the 6th right there. So every time it's x to an even power, it's going to look parabolic in nature. Every time it's x to an odd power, it's going to look cubic in nature. And even x to the 1st power kind of technically looks cubic in nature in that it starts in the top right and then ends in the bottom left. It just doesn't remember to actually curve. Now, as we graph more and more and more, hopefully we start to see a pattern. Notice that all the functions I'm graphing, all the increasing degreed functions that I'm graphing, all of them, as we go to the right, go up and to the right. All of the graphs end up in the first quadrant. Yet, on the left side, some of them go up, some of them go down. But all of them are going up and to the right. Now watch what happens if I change one thing. If I stick a negative in front of every single one of these functions and then graph them, notice the line's going down now. Parabola opens down. The cubic is upside down. Everything is now upside down. Instead of everything going up and to the right, now everything's going down and to the right. We still have some ambiguity on the left side, but the right side all agree. Everyone's going down and to the right. And that has specifically to do with that leading coefficient. Before it was a positive 1, everything went up and to the right. Now it's a negative 1, everything goes down and to the right. We can't say anything for sure about the left side, but we can definitely say on the right side, the leading coefficient is going to give me my direction. So then we can say for any generic polynomial, this is just some representation of a generic polynomial where a, b, c are my coefficients. A would be the leading coefficient. N minus 1, n minus 2, those are exponents. So n would be the degree, n minus 1 would be one less than degree, and so on and so forth. If the a value is positive, that means the right side must point up. If the a value is negative, the right side points down. Notice the leading coefficient tells me nothing about the left side. It only tells me the right side. Positive a, positive right side. Negative a, negative right side. So we had some consistency on the right side based on the leading coefficient, but what about the left side? How do we determine what the left side is? Well, hopefully you may have noticed the pattern on that one as well. This is where the degree of the function comes into play. Let's go ahead and pull that calculator back out. Let's look at these functions again. Remember, y equals x, the degree is 1. The right side goes up because the leading coefficient is positive, and look at the left side. The left side is going down. Now if I change it to x squared, right side is still going up because the leading coefficient is positive, but now for x squared, the left side goes up. X cubed, right side goes up, left side goes down. X to the 4th, right side and left side go up. So hopefully we're again noticing a pattern. As I said earlier, all of the x to the even powers are going to be parabolic in nature. So that means the right side and left side are going to go up if it's positive. Left side and right side are going to go down if they're negative. All the odd degree functions kind of resemble the cubic graph, where one side goes up and one side goes down. In other words, if I plug in a positive number or a negative number to an even power, the result is going to be the same. It's going to be positive on either side. Versus if I plug in a positive or negative to an odd power, the results are going to be opposite. For a positive x, I get a positive answer. For a negative x, I get a negative answer. So the degree doesn't tell me necessarily whether it's going up or down. What the degree tells me is whether the left side agrees or disagrees with the right side. So in general, we can say if the degree is even, then both the right side and left side are going to go in the same direction. Notice I'm not saying they're both going up. I'm saying the left and right side are going to go in the same direction. Leading coefficient tells me the right side. Degree tells me if the left side agrees or not. If it's odd, then the left and right side are going to be opposite. Odd, opposite. So if the right side goes up, then the left side goes down. So those two pieces of information on that single term, that leading term, the leading coefficient tells me whether the right side goes up or down, and then the degree of the polynomial tells me whether the left side agrees or disagrees with the right side. So that tells me the end behavior. But we still have this question of what's going on in the middle? What's going on with my x-intercepts and my behavior around those x-intercepts? And that's going to come down to multiplicity. Now remember, multiplicity is the number of times a zero occurs. Once again, let's investigate a few graphs one by one, starting with y equals x. Now remember, y equals x, linear function. It has exactly one x-intercept at x equals 0. Since 0 is the only solution, that 0 occurs once, it has a multiplicity of 1. Now look at what the graph is doing as it crosses. And let's go ahead and zoom in a little bit closer, just so we can be sure we are seeing what we expect to be seeing. I'm going to change my window -1 to 1 in every direction. So again, we know exactly what we're expecting to see. It's a straight line crossing through x equals 0. But look what happens as I increase the degree. And instead of jumping to x squared, let's go ahead and jump to x cubed. We've got the same basic cubic graph that we always have, that disco guy, up and to the right, down and to the left. But as it crosses the x-axis, we still have the same x-intercept because x cubed has the same solution, x equals 0. But this time, with x cubed, it's not just x equals 0, it's x equals 0 with a multiplicity of 3. And look what happened. It flattened out before it actually crossed through. Well, what if the multiplicity was 5? X to the 5th has the same solution, the same x-intercept, but it has a multiplicity of 5. And notice, it crossed the same way, but it flattened even more. If I increase it to x to the 7th, it's going to cross the same way, but it's even more flat. So if the multiplicity of the 0 is odd, we can see that it's actually going to cross. But as that multiplicity increases, the graph crosses a little bit slower. In other words, the graph hesitates a little bit more. The graph flattens out before it actually crosses through. With y equals x, in other words, multiplicity of 1, it just goes straight through, just like a line does. But on every other multiplicity, as the multiplicity increases, it flattens out a little bit before it crosses through. Now let's go ahead and explore our even powers. If I explore x squared, x to the 4th, x to the 6th, let's go ahead and jump all the way up to x to the 8th and graph those one at a time. So here's x squared, x to the 4th, x to the 6th, and x to the 8th. So once again, as we established before, all of these, because they're an even power, they're parabolic. They all have the same x-intercept, x equals 0. But this time, none of them actually cross the x-axis. They kind of bounce off at that x-intercept at x equals 0. And just like with the odd multiplicity functions, as the multiplicity increases, they get flatter and flatter and flatter as they bounce off that x-intercept. So we have our rule of thumb for multiplicity. If it's an even multiplicity, I expect the graph to bounce off of that x-intercept. It does not cross the x-axis when it has an even multiplicity. When it has an odd multiplicity, it is going to cross the x-axis. It's going to cross from positive to negative, or from negative to positive, wherever it happened to start from. And as the multiplicity increases, the graph flattens out as it approaches the x-axis. And that's true for whether it's an even function or an odd function. So in other words, whatever the multiplicity of that root is, it's going to graph in the same way that corresponding parent function would graph. If the multiplicity of the 0 is 1, then it's going to cross just like a linear function. If the multiplicity is 2, then it's going to quote-unquote cross just like a quadratic function. In other words, it's going to look parabolic. It's just going to bounce off. Multiplicity of 3 looks like a cubic. Multiplicity of 4 looks like a quartic. And a quartic, of course, looks just like a quadratic. Because it's parabolic, it's just going to be a little bit flatter. So based on the number of times that solution appears, based on the multiplicity, we can see whether the graph actually crosses at that x-intercept or bounces off the x-axis at that x-intercept. So now we have all the information we need. Let's go ahead and start graphing. Now remember, we are graphing here. First thing you need to make sure you acquire is some graph paper. Do not do this just on loose leaf lined paper. Make sure you're using graph paper. There's no reason to be completely inaccurate. Let's only be as inaccurate as graph paper allows us. And then second, put away the graphing calculator. Graphs can be done in the graphing calculator. You're welcome to check your answer using the graphing calculator. But when we're graphing by hand, we want to make sure we don't have that crutch available to us that we can kind of cheat without even meaning to cheat by plugging stuff into the calculator. On your test, you will not be allowed to use a calculator on any part of this type of question, so don't practice with a graphing calculator. So let us look at the first one. Now, remember, we're graphing polynomials. This is not a polynomial, or at least it's not written in the polynomial format. This is in the factored format. We've looked at these problems before. It's already factored for you, which makes finding the zeros so much easier. But finding the degree takes a little bit more effort. So first thing we want to do is realize all the things we need to find. We need to know the degree, we need to know the a value, that's our leading coefficient, and we need to know our intercepts. And that's going to be generic for any graph of any family of functions, whether it be polynomials, rationals, exponentials, logarithms, trigonometric. Intercepts is going to be your standard technique for finding a graph. Find your intercepts, connect the dots, there's your graph. Now, depending on what type of family of function, there may be some extra information that might be useful. Polynomial, degree, and leading coefficient is useful, but in general, every type of function we ever look at in this course, we're going to need to find those x and y intercepts. So starting with degree, when it's a polynomial, we can just look at the leading term and identify the degree and leading coefficient that way. When it's in this factored form, it's going to take a little bit more effort to figure out the degree. Now keep in mind, I could multiply all of this through, put it in the polynomial form, and then identify degree and leading coefficient. But there's no reason you actually need to do that, because if I were to multiply it through, the leading term would be based on just the x, the x, the x. The positive 1 and the negative 3 would have nothing to do with that leading term. So if I ignore that positive 1 and that negative 3, this really says x squared. This says x to the 5th. This says 1/2 x. If I were to multiply 1/2 x times x squared times x to the 5th, add up my exponents, I would get 5, 6, 7, 8. I would have 1/2 x to the 8th as my leading term. I didn't actually have to multiply everything out to find out what my leading term is, 1/2 x to the 8th. So my degree is 8, my leading coefficient is 1/2. So these two pieces of information in conjunction tell me my end behavior. The leading coefficient is where I can start. The fact that it's positive tells me that the right side goes up. And then the degree, the fact that it's even. So if the right side is going up, then the left side must also be going up. Next, I can find my y-intercept. Y-intercept's always a super easy thing to find. Just plug in 0 for x and see what happens. If I plug in 0, plug in 0, plug in 0, 0 minus 3 is negative 3, 0 plus 1 is 1. So I would have 0 times 1 squared times negative 3 to the 5th. Well, 0 times anything is 0, so it really doesn't matter what's happening over here. My y-intercept is 0, 0. And then finally my x-intercepts, remember we've done this before, it's just a matter of taking each one of these factors, setting it equal to 0. When it's already in its factored form, this is super easy. 1/2 x on the outside, that's going to represent an x-intercept of 0. X plus 1 gives me negative 1. X minus 3 gives me positive 3. But remember, as we do this, let's also take note of the multiplicity. X equals 0 came from this factor right here, x to the first power, so its multiplicity is 1. Negative 1 came from x plus 1 squared, so its multiplicity is 2. And the multiplicity of 3 is going to be 5 based on its factor. So x equals 0 appears once, x equals negative 1 appears twice, x equals 3 appears 5 times. So based on its multiplicity, I know what's going to happen on the graph. X equals 0 has a multiplicity of 1. So as the graph approaches x equals 0, it's going to resemble a line, y equals x, x to the first power. It's going to cross straight through. Negative 1, since it had a multiplicity of 2, is going to resemble a quadratic. In other words, a parabola. As I approach x equals negative 1, I'm going to bounce off that x-intercept. I'm not going to cross. I'm going to bounce just like a parabola does. And then x equals 3 is going to resemble x to the 5th, which is really just a slightly flatter version of x to the 3rd. It's going to resemble a cubic, just a little bit flatter. So I'm going to cross through at x equals 3, but I'm going to flatten out a little bit as I do it. So let's see what that looks like. I can go ahead and start by plotting all of my intercepts, all of my x and y intercepts. And then I'm going to remember my end behavior. Based on the leading coefficient, I know the right side was going to go up. And based on my degree, I know the left side was going to agree. Now, I like to graph from right to left because of my leading coefficient test. The right side is where I first determined which way the graph was going. I like to graph in that direction then. So one place in mathematics, instead of going from left to right, I like to go from right to left. Although if you go from left to right, it really doesn't matter. So as I go from right to left, I'm approaching this first x-intercept at 3. Now remember, the multiplicity at 3 was 5, so I know as I cross over x equals 3, it's going to flatten out first. So I'm going to aim a little shy, flatten out, and then cross through. And then of course I can connect that to my arrow up here, smooth it out nice and neat. Now my next x-intercept is right here at x equals 0, so I know I'm going to need to dip down and then back to get to x equals 0. Question is, how far down should I go? Should I go all the way down here, or should I make it a little bit shallow? And here, I really don't care. It doesn't matter to me how low you go or how shallow you go. I'm not going to be looking at how accurate your graph is. I'm going to be looking at where your x-intercepts are. I'm going to be looking at how you cross those x-intercepts. And I'm going to be looking at the ultimate direction. So as long as you go down somewhere, it really doesn't matter to me. If you're going up, we've got a problem because then you didn't cross the x-axis like you should have. But as long as you're down here somewhere, it really doesn't matter. So at x equals 0, I know the multiplicity was 1, so that tells me I'm going to cross straight through. I'm not going to bounce off. I'm not going to flatten out. I'm going to cross straight through because the multiplicity was 1. So let's go ahead and connect that to the graph. And then my last x-intercept was at negative 1. Its multiplicity was 2. Therefore, at negative 1, I'm going to bounce off. It's just going to bounce right off the x-intercept at negative 1 and then head up to infinity and beyond. So I'm going to bounce it and then head all the way up here to my arrow. So there's my wonderfully, beautifully, perfectly smooth and curved polynomial graph. So feel free to smooth these things out, erase what you need to erase to smooth it out, but this is going to be the basic shape of that curve. Now, just like I said earlier, feel free to pull out a graphing calculator to check your answer. I can pull out a calculator, I can type in the function 1/2 x, x plus 1 squared, x minus 3 to the 5th, and graph it. I'll go ahead and make sure I'm back to my standard viewing window before I graph it. Now notice though, when I graph it, I'm usually not going to get a very pretty picture. I may have to zoom in a bit before I get something that resembles what I actually graph. Now first off, I'm going to notice at x equals 3, I see it crossing just like I expected it to cross. It kind of looks like a cubic S-curve or a quintic S-curve. It's crossing at negative 3, but it's flattening out before it crosses. Now this guy up here, if we zoom in a little bit, actually let's change our window. We don't need to go from negative 10 to 10. Since my largest x-intercept is at 3, why don't we cut it off at 4? And my smallest x-intercept is negative 1, so why don't we cut it off at negative 2? See what that does. Notice when I condensed my x interval from negative 10 to 10 to negative 2 to 4, it kind of stretched horizontally my graph, and I can see things a little bit better. So notice it's crossing at negative 3, flattening out. Now it went down much further than I did on the graph, but that's fine. But I can see it coming back up here and crossing straight through at x equals 0, going way higher than I actually did on my graph, and then coming back down to negative 1 and bouncing off. So based on what I see on my graph on the calculator, I can say that my hand-drawn graph is sufficient. So it's not perfect. I never expected it to be perfect, but I know my x-intercepts are correct. I know I'm crossing and bouncing the way I'm supposed to. I know my end behavior is correct, so I'm happy. All right, here's another one to try. Why don't you try this one on your own? Hit play when you're ready. All right, so once again, we're going to go through identify all the relevant information. We'll start with degree. There's no x's on the outside. I just have x cubed and x squared, so that's going to be a 5th degree polynomial. Leading coefficient is going to be -4, which means it's going to be opening down and to the right. Since the degree was odd, it's going to be opening up and to the left. So they're going to be opposite of each other. Right side goes down, left side goes up. Y-intercept, let's plug in 0 for x. This time it's not going to be as easy as it was last time because there's no x on the outside to cancel everything else out. I actually will have to do a calculation. I'll have -3 to the third, which is -27, 2 to the second, which is 4. So what I have is -4 times -27 times +4. So I know my y-intercept is positive. Remember, don't pull out the calculator. Just do some scratch work off to the side. 4 times 27 times 4, or 16 times 27, you're going to get 432. So I have my y-intercept of 0, 432. And then the x-intercept, just pulling them right out of the factors, is going to be x equals -2 and +3. Keeping note of their multiplicities, +3 has a multiplicity of 3, so it's going to cross, but it's going to flatten at x equals 3. And at -2, it's going to bounce just like a parabola does because of the even multiplicity. So once again, we'll go ahead and plot our x-intercepts and our y-intercept, but this time our y-intercept is at 432. If I try to count up to 432, I'm going to need a lot of graph paper. Easy solution to that, just don't count by ones. There's no reason you have to count by ones. Feel free to label your axes however you wish to label them to make things easier for you to graph. Instead of counting by ones, why don't we count by 100s? But I can't just assume that I'm counting by 100s. You have to label your axes based on your scale. If you don't label it, I assume you're counting by ones. So I'm going to go ahead and label it with a 100 right here. Therefore, 432 would be somewhere roughly around here. Now we're ready to go ahead and draw our graph. Remember, we determined a second ago that the right side was going down. So I'll draw an arrow down here to remind me the right side goes down. And then the left side disagreed because it was a 5th degree polynomial, so the left side goes up. As I cross each x-intercept, I'm going to cross according to its multiplicity. At x equals 3, the multiplicity was 3, so I'm going to cross, but I'm going to flatten out as I cross, just like a cubic graph does. Let's go ahead and connect that to the arrow down here. Now my next intercept is at -2, but before I get to -2, don't forget to actually cross your y-intercept. And at -2, the multiplicity was itself 2, so it's going to bounce just like a parabola does, and then head up to my other arrow. So there's my nice smooth polynomial curve, flattens out at 3 but crosses, bounces at -2. Once again, feel free to pull out the calculator to check your answer. We'll type in the function. This time I'm going to go ahead and pre-adjust my window. The intercept furthest to the left was at -2, so let's go ahead and change this to -3. And the intercept furthest to the right was 3, so let's keep that at 4 and then graph it. So once again, it's not going to perfectly resemble my hand-drawn graph. I do see it starting on the bottom right, crosses at +3, but flattens as it crosses. It's going to go way up to 432. And you know what, let's go ahead and adjust our y max to, let's say, 500. And again, counting by 100s. Let's go ahead and go down to -100 on the y-min. And hey, look at that. We got a pretty good resemblance to the graph that we drew. Started again, bottom right, flattens out, goes up to 432, bounces off -2, and goes up. So based on my calculator, I can see that my hand-drawn graph was correct. I didn't start with the calculator. I started with the hand-drawn graph. I'm simply using my calculator to check my answer. All right, here's another one for you. Now, as we approach this one, let's notice that it's no longer in the factored form, it's in the polynomial form, which makes some things a little bit easier and some things a little bit more effort. For instance, the degree, we don't have to add up anything because we're not multiplying anything through. The degree is just 3. We can look at the leading term. This is a third degree polynomial. And once again, the leading coefficient is right there. We have a leading coefficient of 1. So we can very quickly and easily identify that the right side goes up, and the left side, since it's odd, must be going down. Our y-intercept, even easier now, because it's in its polynomial form. If I plug in 0, plug in 0, plug in 0, anytime you have a polynomial, the y-intercept is just whatever the constant term is. So in this case, it's 0, 100. The only thing you really have to work for when it's written in this full polynomial form is that x-intercept. To get the x-intercepts, we're actually going to have to factor this out in order to solve it. So why don't you take a moment, go ahead and factor this out so that you can solve it. Keep note of the appropriate technique for this type of problem. That's what we've spent the last 3 lessons talking about. Once you have that, go ahead and hit play so we can continue. All right. So we need to be able to solve this, so we're going to start by setting it equal to 0. Remember, our generic technique that we should always look for first is GCF. I don't see anything in common between all 4 terms, so pulling out a GCF is not going to be helpful. I can then attempt to see how many terms we have. We have 4 terms, so quadratic techniques are not going to be useful. Basically, it's going to come down to grouping or the rational root theorem. Let's hope that grouping works. I can determine if grouping works by looking at my ratios. Right in here I have a ratio of 1 to 4, and then 25 to 100 is also a ratio of 1 to 4. So that means grouping is definitely going to work. So out of the first pair I can pull out x squared, that leaves x minus 4. Out of the second pair I can pull out a negative 25. Anytime you have a leading negative, pull it out, and it also leaves x minus 4. Now I'm not done factoring until I have a quantity times a quantity. Right now I have an entire quantity minus an entire quantity. I notice between this individual term and this individual term I have x minus 4 in common, so let's factor out x minus 4 even further, and that leaves x squared minus 25 behind. So here I have a factored version of the polynomial. Now I could factor even further. The x squared minus 25 would be factored into x plus 5, x minus 5, but that's really up to you if you want to do that. It's not really a necessary step because I can tell right from here that my solutions are going to be positive 4 and positive and negative 5. I don't need to factor this out further to know that those are my solutions. So I have x-intercepts at 4, positive 5, and negative 5. I have a third degree polynomial. I have 3 x-intercepts. So that not only confirms that I have all my solutions, it also implies my multiplicity. If I have 3 solutions for a third degree polynomial, I have a multiplicity of 1 on each solution. Also, because each factor appeared only once, even the positive negative 5 was from x plus 5 appeared once, x minus 5 appeared once. Each solution appears only once, which is going to make my graph super easy. Because each multiplicity is 1, I'm just going to cross straight through on every single x-intercept. So we can go ahead and plot our x-intercepts, negative 5, positive 5, and positive 4. Y-intercept was at 100, so I'm going to change my scale. I'm going to change it to 20 so that 100 would be at the 5th mark. Leading coefficient was positive, so I'm going to be going up and to the right. It was an odd degree, so I'm going to be going down and to the left. And again, at each x-intercept, I'm going to cross. I'm going to start out positive. I'm going to cross. I'm going to cross. I'm going to cross. So it's just a matter of starting in the top right, snaking all the way through, close enough, connecting there, all the way up to my y-intercept, connecting one more time, close enough, and all the way down. Perfect. And once again, I'll pull out my calculator to check my answer, type in the function. I'm going to go ahead and adjust my window in advance. I'm going to go from negative 6 to positive 6, since that would include all of my x-intercepts. And my y-intercept was 100, so I'm going to go from negative, let's go from negative 50 to 150. Counting by 20s again. So there we go. I didn't get it perfect, but I didn't need to get it perfect. I started in the top right-hand corner, crossed at 5 and 4, intercepted at 100. I actually was supposed to go up a little bit further, but I didn't know that, nor did I need to know that. And then I crossed again at negative 5. So my nice smooth snake curve, perfect. All right, here's another one for you. Hit play when you're ready. All right, once again, it's in its polynomial form, so we can very quickly identify the first 3 pieces of information. The degree is 4, the leading coefficient is negative 2. Negative means the right side goes down. Even means the left side agrees. Y-intercept, there is no constant term, so I have a y-intercept at 0, 0. Now to get the x-intercepts, let's set it equal to 0 and solve. Factor out a negative 2x squared. That leaves behind x squared minus 1. That could be factored further to x plus 1, x minus 1, but I don't feel a need to do that. Negative 2x squared equals 0 is going to produce a solution of 0, but of course it's going to have a multiplicity of 2. X squared minus 1 is going to give me plus and minus 1. Positive 1 has a multiplicity of 1. Negative 1 has a multiplicity of 1. So I have 2 answers here, and technically 2 answers here for a 4th degree polynomial. So I have everything I need to know. Both sides are going down. Y-intercept at 0, x-intercepts at negative 1, 0, and positive 1. So plot my intercepts. Again, left side, right side going down. I'm going to cross at 1 and negative 1. I'm going to bounce at 0. So let's see what that looks like. Again, right side starts down. I'm going to approach negative 1. I'm going to cross straight through. I'm going to bounce at 0. And then I'm going to cross straight through at negative 1 and go straight down. So I have my little M-shaped graph for my quartic polynomial. And as we've done for all the other ones, let's go ahead and check our answer. Graph it in the calculator. I'm going to adjust my window before I get started. I'm going to go from negative 2 to positive 2 to include everything. I don't need to go nearly as far on my y value, so I'm going to go from negative 5 to positive 5. Back to counting by ones, and graph it. Cross, bounce, cross. So again, sketch is not perfect, but it's good enough to match what it needed to match. All right, one more. Hit play when you're ready. So as always, degree super easy. That's going to be 5th degree, leading coefficient of negative 2 again, which means once again the right side is going to go down, but this time the degree is odd, so the left side is going to go up. No constant terms, so another y-intercept at 0, 0. Let's find our x-intercepts. So first technique we should always try is GCF. I notice that there's an x on every single term, so I can pull out the x. I have a leading negative, so I'm going to factor out that negative. And all 3 coefficients are even, so I'm going to pull out negative 2x. That's going to leave behind x to the 4th minus x squared minus 20. So that negative 2x is going to produce a solution of 0. This time it's x to the 1st power, so that 0 is going to have a multiplicity of 1. So I know my graph is going to cross at x equals 0, just like a line crosses. Now let's go ahead and continue with this guy. This time we have a 4th degree polynomial, but it's in that quadratic form. So let's go ahead and factor it just like we factor quadratics. X to the 4th can be broken into x squared and x squared. Factors of negative 20 that add to negative 1, well that's just going to be negative 5 and positive 4. X squared minus 5 produces x squared equal to 5, or x equals positive and negative square root of 5. Each one of those solutions only appeared once, so each one has a multiplicity of 1. We'll do the same thing on x squared plus 4, so x squared equals negative 4, so x equals positive and negative 2i. Now on these sets of answers, some of us might get a little worried. Square root of 5, where is square root of 5? Well, isn't it just a little bit further than the square root of 4? And for that matter, isn't it just shy of the square root of 9? Square root of 4 and square root of 9 is really 2 and 3. So the square root of 5 is just anywhere between 2 and 3. Remember, we're just graphing this by hand. We don't have to be perfect. Square root of 5 is roughly 2 point something. I really don't even care what that something is, even though it happens to be 2.23. I don't need to know anything specific. I just need to know that the square root of 5 is just a little bit more than 2. As for 2i and negative 2i, here we get to the point to realize we are graphing on a real number coordinate plane. 2i is an imaginary number. If you want to plot an imaginary number, you need an imaginary plane. Therefore, 2i has no place on this graph. 2i does not make sense for the context of this problem, so we're just going to ignore it. Anytime you get imaginary numbers when you're graphing, just ignore them. So we only have 3 x-intercepts, 0, positive root 5, and negative root 5. So when we plot them, again, we'll plot at 0, and then square root of 5 is just a little bit more than 2. Negative root 5 would be a little bit less than negative 2. I don't have to plot anything for the imaginary numbers because they don't exist on a real number plane. So remember, this was a 5th degree polynomial and it started out negative. So again, the right side is going down and the left side is going to be going up. Since each of those intercepts only appeared once, I'm going to cross straight through each one ending positive. So here's my nice, smooth snake curve. So once again, let's pull out our calculator to check our answer one final time. So I've got the function typed in here just as before. Once again, I'll adjust my window. I'm going to set my minimum and maximum to -4 just to make sure everything is clear. Hit graph. Notice it went down, it went up, and it went down at roughly at square root or 2 and change, -2 and change. It's going through 0. It's going straight through every single time. But let's go ahead and adjust. Let's go ahead and zoom out a little bit. Increase our y values just so we can get a better view of the graph. Instead of going -5 to +5, let's go all the way to 100 in either direction just to get a better view. So it went down, up, and down, just like the graph that I drew if you use your imagination. So next time we're going to go beyond polynomial functions. We're going to start at looking at rational functions. A lot of the techniques are going to be the same because of course a rational function, which means a fraction, is just a polynomial divided by a polynomial. So a lot of the techniques that you use in here are also going to be used in the next lesson. Stay tuned.